now that you all have had an opportunity to have a break and absorb the first two Gilbreth lectures, and I can tell by the volume of the conversation that continues that the whole thing is very, very exciting and has captivated you very well. Certainly has me, as a matter of fact. So now our next presenter, Todd Coleman, is an associate professor of bioengineering at UC San Diego, and he's co-director of the Center for Perinatal Health. His research is highly interdisciplinary and at the intersection of mathematics, scalable machine learning, bioelectronics, and medicine. Current applications of those synergies include perinatal health, chronic disease management, and cognitive monitoring during aging. Dr. Coleman received his bachelor's degree in electrical engineering and in computer engineering from the University of Michigan, his MS and PhD degrees in electrical engineering from MIT. The title of his talk is Smart Skin Sensors and Analytics in the Cloud to Advance the Frontiers of Wearable Health. Please welcome Todd Coleman to the stage.
So as I set up, I was really excited to hear what Bob Dine said earlier about the Bell Labs Fellowship. Quite a few people that have mentored me while I was a graduate student were recipients of that fellowship, and it's an absolutely amazing program that they created and how well it mentored so many women and underrepresented minorities. And we should all applaud what Bell Labs did and encourage current technology companies that have monopolies, such as Google, to try to follow in their footsteps. So I thought I would give my talk by telling a story, and where the story begins is when I did my graduate studies. I did my graduate studies with Professor Muriel Medard, the lady you see at the bottom right, and I was trained by her in a lot of applied mathematics, probability and statistics, the type of math that's underneath how your cell phone works. And so with that, I was on my way to take a faculty position at the University of Illinois in the cornfields, and she gave me the best piece of advice in my career. She told me to delay my start date, call up my boss, the department chair, and tell him I want to first do a postdoctoral study in something wildly different, is what she told me. And so I was very fortunate to turn around and do something wildly different by working with a gentleman you see in the top right, Emory Brown. And Emory's a very unique gentleman. He's an anesthesiologist, practices medicine in Boston. He's also a professor of neuroscience at MIT. And why I particularly was very excited about working with him is that his PhD is in statistics, so we had the common language of thinking about statistics to take what I had learned in my graduate work and apply it towards medicine. And I'm very excited to say that Emory just learned today that he was elected to the National Academy of Engineering, and he's one of about 20 people in the world that's a member of all three national academies. So I'm very proud of him, very happy for him. So with that, I took sort of my training in electrical engineering and analytics with neuroscience, and I got to Illinois, and I went to work on something fun and something different, take a risk. And so what I got interested in are applications that lie at the intersection, things such as brain-computer interfaces, some of you may have heard about, systems that create a direct communication pathway between the brain and the external device. And so, for example, if you see this gentleman in this picture, he has something that looks like a shower cap on his head. And that system is basically multiple electrodes. You scrub the skin, you apply conductive gel, and you can record the electrical rhythms of the brain. And it turns out that when you're engaged in things like imagining left or imagining right, the pattern of voltages are different. So as you see, when someone imagines his left hand, they're sort of red on the left, blue on the right, and the opposite occurs in the other domain. So the patterns of the voltages are swapped. And so what that means is that if we can take this understanding of neuroscience and then do appropriate data analysis, we can build a platform where we can perhaps extract a bit out of your brain. You imagine left or imagine right, we record these signals, we can output something like the likelihood you're imagining left or right. And so this could be useful, first of all, because it's cool, right? But secondly, if we think about people who came back from the war, who have a spinal cord injury, their brain is still intact, but the pathway to their bodies is severed, someone who's a stroke survivor, there's a variety of applications where using this technology can do good. So this is all cute and dandy, but it turns out after a while, this gets pretty boring. It's pretty underwhelming, right? You're either moving a ball to the left or moving a ball to the right with your brain. And so we realized that, and we had the epiphany that suppose that I can get, a sequence of bits out of your brain. How can I do things that are more interesting? What we realize is what we need to take advantage of is the appropriate use of feedback. This is one of the most important things you will learn as engineers. And so the idea that we had is that what if we could play some type of question and answer game with the brain? And so let's imagine that you have some intent in your head and the computer is trying to help you accomplish that goal. It can ask you a question, you give it a binary response. And so we all know how to play 20 questions. You have a number between 1 and 20 in your head. A very dumb thing for me to do is to ask you, is a number less than 19 or greater than 19? And then ask you, is it less than 18 or greater than 18? A smarter thing to do is to first ask you, is it less than 10 or greater than 10? You tell me it's less than, then I ask, is it less than 5 or greater than 5? Then we zoom in very rapidly. So we took that same type of idea, but had to develop new math to now do it when it's not a number between 1 and 20, but it's something in a continuum. Let's imagine you want to specify the path that you want your wheelchair to go. And so we had to develop new math to do that because in addition, we're extracting noisy signals reflective of that. But after we optimize all the math, what you end up with is a very simple workflow where that little gray thing that you see is the path that's in the person's head. And all we're doing is we're asking questions by showing another path. And all you have to do is to do a mental comparison is how does one path compare to the other? Look at the first location where the two paths differ. If it's counterclockwise, imagine left. If it's clockwise, imagine right. And that has very nice properties, and it's very, very efficient. It's, in fact, the most efficient that you can be. And most importantly, you see it works. You see that the path that's partially black and partially red, slowly but surely, is honing in on the gray path. This is from brain signals. Noisy stuff. It's pretty remarkable. So we went one step further, and I was on my way to give a talk at Princeton. And so we want to overlay this on top of Google Earth technology. So what's under the hood is the same. I'm just changing the skin. And so in this example, I'm trying to specify a path from San Diego to Princeton, New Jersey. This is the path that it shows to me. That's like asking the question, is it less than 5 or greater than 5? I see that the correction is in a clockwise orientation. So I imagine squeezing my right hand. The system is doing analytics underneath this. And with time, what ends up happening is it ends up honing in on the path that was in my brain through this question and answer game, basically an analogy of 20 questions. And so with this, we wanted to go one step further to really communicate to the people in this community, this new emerging community of brain-computer interfaces, that it's not just about extracting bits, it's about asking the right questions. So we wanted to develop something that will be very difficult to use if you didn't use feedback appropriately. Can we fly a remote control airplane over the cornfields of Illinois? That was our objective, and so we partnered with the aerospace engineering professor, and we did that. And so what you'll see in this video is a gentleman that has this shower cap on his head, and again, it's just this very simple question and answer game that's playing with him. But in the background, this plane is flying. You can see the cornfields, the camera feed flying over the cornfields. And what the plane is doing is it's just using a motion planning algorithm and going along the path that he's sequentially specifying. And so this is very fun and very exciting, but this is not to suggest that in the future people will be flying planes with their brain. Rather, we deliberately want to be provocative to tell people about the importance of using these principles in these applications, and you could do things that you perhaps thought you could not otherwise. And I think that this is perhaps best exemplified in this article that appeared in The Economist. This is something some of your parents read. And so they have a technology quarterly, and they had an article called Put Your Thinking Cap On, pun intended, talking about things that we used to think were fables or hoaxes or science fiction are now fast becoming a reality. So I was like, great, this is confirmation of the stuff that I've been working on. And so we get pretty excited about that, but if you stand back and you take a look at this picture, this is exciting from a Steve Wozniak perspective, but this is underwhelming from a Steve Jobs perspective. And that's because you have to have the shower cap, there are wires everywhere. This is something that's kind of cute, but it perhaps will not really make its way outside of the laboratory. And so at this moment, if you stand back and take a look at where we are, we developed some innovative approaches to wed the two paintbrushes, right, of analytics that I learned in my graduate work and medicine that I learned in my postdoc work. And we can develop some rather cute paintings, but if we really want to do things that can have impact, we have to move out of our comfort zone. And so I realized that we need to innovate with how we're acquiring these signals and do innovation with sensors. And by wetting these paintbrushes together, we can make better paintings. And so what that leads to is sort of the perspective that I have right now being at UC San Diego that as a medical school, and there's a variety of applications that we can imagine where we can extract information from the human body, really important, in a manner that does not perturb your normal daily life. We can do appropriate analysis of that information so that we can hand that to a decision maker, such as a doctor, to help you in case there's a problem or to provide suggestions back to you. And so I'll speak to a little bit of this in our talk. And I'll begin with how we have developed some innovations as it relates to that paintbrush of the sensors. And so where it sort of begins is very much along the same lines of the talk of the previous speaker, is that we have, what we know is that biology is soft and curvy, linear, and elastic, but electronic circuits, everything that's inside of your smartphone, are built on top of semiconductor wafers, and those things are rigid, planar, and brittle. If you try to bend them, they break. So we have a fundamental disconnect, kind of like Democrats and Republicans, or Michigan and Ohio State, all right, as me a Michigan man. So the high-level idea, and we established a partnership with an expert material scientist at the University of Illinois named John Rogers, who's a member of the National Academy. The high-level idea is that can you take electronic circuits that are built on these rigid wafers and realize that only the very top layer of the wafer has where all the circuits are. So can you develop a clever way to peel off the top layer, and then you can mount it onto something that's naturally bendable? And so it turns out that you can do that. You can develop a process where you take a stamp-like material, peel off the top layer, and then you can mount it onto whatever you like. And so with that, I engaged John about my excitement of perhaps mounting this onto the skin so we could monitor the electrical rhythms of the brain. And so we partnered together to do electrophysiology monitoring. And what you see is a picture right here. It's a system that's called epidermal electronics. The epidermis is the outer layer of your skin. And so what you can see is that it's flexible, it's electronics, it's biointegrated. You can use a variety of materials to mount it onto the skin, including a temporary tattoo. And so what you see here is the backside of a temporary tattoo. You can transfer the electronics from the wafer to the backside of the temporary tattoo, then mount it onto your skin, and again, it can bend and compress with the skin. We demonstrated this in 2011. Here's a blow-up picture of the system demonstrating that it can do many things. And the high-level idea is that because you're leveraging silicon, you can take all the benefits of silicon. So you can mount antennas on these things that transmit at the same frequencies as Bluetooth. You can deliver power to these things wirelessly, the way your Android smartphone works with NFC. You can put LEDs and light sensors on there so you can monitor things like blood oxygen. You can monitor mechanical bending and strain, what the previous speaker spoke of. You can monitor temperature, as well as the bread and butter, what I got excited about, electrical rhythms of the body. And so here's just a demonstration of some of the things that we can do. We can monitor the electrical rhythms of the heart, the EKG. You can monitor skin temperature. And what you see at the bottom are the electrical rhythms of the brain. And what you see in the bottom right is that it turns out that when you close your eyes, there's more energy in about the 10 hertz band, and you can see that, where there's more energy there. And then when you open your eyes, it goes away. So that was a nice demonstration when we were at Illinois in the lab. And as I moved on to being at UCSD, I wanted to go from the benchtop to the bedside to really try to validate this in a clinical setting where this really could be useful and help save lives or help in decision making. And so what we got interested in is the scenario of pregnancy monitoring, right? So when a woman is in labor, there's basically a couple things that they measure: her uterine contractions, her fetal heart rate. They have to measure this to make sure the baby is not undergoing distress. And so what we did is we partnered with an MD at UC San Diego who delivers babies, and along with the conventional clunky belts, we put a multi-electrode array of these sensors on there and developed the analytics type of stuff that you do. And here's just a picture demonstrating the red represents what you get from the clunky belt pertaining to fetal heart rate, and the blue is what we can estimate with our algorithms using this unconventional technology. So you might ask yourself, well, in America, I mean, who cares? People deliver babies in the hospital. What's wrong with the belt? Well, where this could be useful is twofold, one of which is, let's imagine now that 10% of babies born are born premature. We don't know why. Let's imagine that a woman is at risk has an at-risk pregnancy. We might want to monitor at home. She doesn't want to have those clunky belts. She wants something less obtrusive. Secondly, let's think about the developing world. There are many parts of the developing world where there's literally more smartphones than there is running water. And so you have the capability to have something unobtrusive and cheap, and a midwife can measure this information and pass it to a doctor 1,000 miles away. It creates many opportunities to have safer pregnancy monitoring and delivery. So this is one example. We have many. And with this, we got interested in pretty fast. We got involved in a variety of different clinical projects at UC San Diego. And this workflow of how you do this fabrication, it works, but it turns out that there are sometimes issues with its scalability. We have to do everything on this wafer. We have to dip it in nail polish remover, acetone, develop an intermediate stamp-like thing that presses down on it, peels it off, and then mount it onto something flexible. So as you can imagine, this ends up taking a lot of time, and we got interested in developing a different way to do that. And so we did what's called making the tail wag the dog. And our high-level motivation was that what if we could get our stuff compatible with things such as the printing press that allow for massive scalability, the way that they print many New York Times papers. And so our graduate student Day, brilliant gentleman, basically figured this out. And so this is unpublished. You guys are some of the first to see this. But what he's done now is he's changed how he deposits things on the wafer. And the key thing he wants to do is to eliminate the need to use any type of chemical or that intermediate stamp. You directly take what you want to mount it on, and you just press down on it. It's an adhesive, and it can peel the sensor right off of the wafer. And so that little material right there is Tegaderm. It's made by 3M. It's used in hospitals everywhere. It's already FDA approved, optimized for the skin. You can directly take it and peel it off. As I mentioned, wafers are brittle, so we wanted to go one step further to see that, do we even need to deposit this on wafers, or could we directly deposit this onto flexible materials to really create the picture like the left? And you guys really are the first to see this. This was just accomplished yesterday. But in this video, what you see is that they now have deposited the stuff on a different type of material. And again, he's pressing down with this adhesive. Notice everything here is flexible. There's no brittle wafer anywhere. He can press down on it, and it comes right off. And so we're very excited about that because this can create the opportunity to do things like the picture that you see in the left that creates much more scalability. So one of the important things that we care about as engineers, not just getting something to work, but getting it to work at scale. And you see he can peel it right off. So that's one type of innovation that we got involved in, and that relates to being able to measure the electrical signals from the body. But as we all know, our smartphones have processors in them. They take things, they process them, and they do things with them. So not only do we want to be able to sense information, but we want to be able to process it. And rather than needing to design all of those details on the wafer ourselves, what if we could rely on other smart people who have developed specialized chips and spent millions of man-hours, like Texas Instruments or Broadcom? What if we could take their chips, or Qualcomm, sorry, Andy, we could take their chips and we could embed them into something that's aggregately flexible. And so our graduate student Yunsong has developed a way to do that. And the key thing that's important right here is that if you take a look at that small little chip, it's smaller than basically a speck of dust. And we can integrate that into something that's aggregately flexible, and we can leverage all the optimization that other people have done. And here's a very simple video. This stuff is also unpublished. We'll be publishing soon. And what you can see right here is a totally functional system. That little module in the middle is a Texas Instruments chip with millions of transistors. And our grad student has developed a way to integrate this into a flexible substrate. And you can see the LEDs blinking and everything else. And we can take this off of that glass slide and make it flexible. So that's the story that I wanted to tell as it relates to innovations with sensors. That's some of the things that we're doing, but we by no means are wed to what we're doing. We're interested in any innovations that people are taking so that we can measure things from the human body that are important to help us make better decisions in a manner that's unobtrusive. Now, the next question that becomes, let's imagine that you build the most sophisticated temporary tattoo in the world that can extract information. Ultimately, if it doesn't help people make decisions, if it doesn't help us save lives, it's useless. And so part of that is how do we extract meaning out of this data? And the workflow as it works right now, a lot of us know that there are Fitbits and Jawbones and things that exist right now. The typical workflow for how these things work is they extract data. This is one of these Samsung watches. Okay, so they record multiple different aspects of your bodily function, your heart rate, your blood oxygenations, so on and so forth. They digitize all the information, then they wirelessly transmit it. They wirelessly transmit it to the cloud, right, such as your Google accounts, all of that stuff is stored in the cloud, and they do some basic processing. And basically what a lot of people are doing right now in digital health is they're using the exact same algorithms that Google and LinkedIn use to serve ads to you. And the high-level idea of what they do is that there are many explanations of what takes place, and they want to find the one that's the most likely, right? And what you see in this blue curve and this green curve, the red dot is the highest point. But what you notice is that if you're just finding the most likely explanation, you don't know if you're on the blue curve or the green curve, because all you have is the red dot. So we know that clinicians really care about uncertainty. You need to not only have a good explanation, but also uncertainty. So our graduate student, Diego, has developed a clever approach to be able to also quantify uncertainty using the existing infrastructure, resting on top of things at scale, such as what Google does. And with this information, we can significantly improve outcomes, such as whether or not you're going to die. We can predict whether or not you're going to die in an ICU based upon a variety of different measured physiologic information. So that's the good news. The bad news is that a lot of these wearables, it's kind of like your smartphone when you have Google Maps on. It eats a ton of energy. And so we very rapidly began to notice this, that if you're in any situation where you're doing continuous monitoring, streaming this data, this is all cute and dandy, but this workflow doesn't work. And what we got interested in is changing the workflow where maybe right inside of your wearable, you do all of the processing and a lot of the statistical analysis right there. Rather than transmitting all the raw data, just transmit the statistics. And our graduate student, Marcella, has recently done that. And we can actually recreate what we did in the cloud locally on some of these new chips that have lots of processing power. And this can significantly improve performance. That's the high-level picture. And so with that, I will now pivot on in talking about not just the analytics aspect, but give you an example of a concrete clinical application where we use this. And where this story starts is with what I call trickle-down technology. And so it turns out that in many practices of medicine, as well as in many technologies that are developed for medicine, things are typically optimized for adults. They take a subset of that which works in children, and they just directly apply it. They take a subset which works in newborn babies, directly apply it. But seldom do they develop medical practices or technological innovations that are specifically tailored to arguably our most vulnerable patient population, newborns. So I learned this on accident, drinking margaritas with some MDs on my birthday in 2011. And I met this MD right here named MJ Harbert, and she's one of about 30 people in the world that has her specialty. She is a neurologist, but she is a neonatal neurologist. So she basically has an expertise in understanding and treating a brain injury of newborn babies. And it was fascinating, some of the things that she told me. And basically, the way the brain functions for a newborn baby is very different than that of an adult who has a stroke. And so we have to really tailor our work appropriately. And that's what this sentence says. The physiology of the newborn baby is very different from a 3-year-old, let alone an adult. And it turns out that one of the things that's very common for newborn babies, they don't have the negative feedback connections in their brain that control. They form the last. And remember I said that 10% of all babies born are born premature. So if a baby is born premature, you don't have that feedback, what's going to happen? Instability. What does instability mean in the brain? It means seizures. So it turns out that many newborn babies, especially premature babies, have brain injury, which results in seizures. And if these seizures go left unkept, it can lead to long-term cognitive impairment. It can lead to long-term epilepsy, a variety of problems. And so so she needs to aggressively monitor these babies because she can actually do medical interventions that are specifically tailored to newborns. It turns out she can cool their core body temperature down. By cooling the temperature, you basically loosen the swelling, and this has very good outcomes in newborn babies. But a lot of these babies, you wouldn't even know that they had a seizure. There's nothing about their behavior. They're not jerking. You need to be monitoring their brain waves continuously to understand if your intervention is working. So she needs to be monitoring their brain. But if you look at that picture of that baby right there, he doesn't look happy. The reason he doesn't look happy is because he has basically the same shower cap that I showed you before. Now, babies are particularly vulnerable, especially premature babies, because the skin is not totally formed. That process of scrubbing the skin and applying the gel can lead to inflammation, infection. A baby can die from this, and this happens. So you can sort of imagine where we're going with this. We got curious about testing. Could we use new types of sensors that are more unobtrusive, that don't require the scrubbing of the skin, again, in a validation study? So what you see on this newborn baby that has a brain injury, the conventional electrodes are here, and then we put the epidermal sensors here, and we want to do a validation study. Compare the black waves to the red waves. Red are conventional, the black is a new technology. Are they similar? But that's not the only thing we want to do. We also want to assess what effect does this have on their skin. And so what you see in the picture in the bottom right, the red is where the conventional electrode was, and the black is where the epidermal sensor was. And if you notice carefully, you can see there's a lot of redness near where the conventional electrode was, and there's not as much for the other. So this was the first premature baby that we worked with. This is ongoing work, unpublished, but we're very excited about it. So more broadly, as was mentioned when I was introduced, little by little, from the pregnancy monitoring to the newborn baby monitoring, what we realize is that there's a theme right here of wedding engineering and medicine to this window of when a child is born, and that's what perinatal means. Pregnancy, right at childbirth, newborn baby. And so we collaborate with people on the pregnancy side, the newborn baby side, as well as pediatrics, and we're very excited about this because this is an institute of engineering and medicine, and it forces MDs and engineers to work together. You can't work separately. And this really increases the likelihood that we will have effective collaborations that really result in improving lives. And so this is the high-level story that I would like to tell. And I would like to thank some of the people who supported us. We're very thankful to Intel, to Qualcomm, as well as to Broadcom, who have donated some of their technology for us for a variety of the different projects that we've worked on in terms of hardware. And we also would like to thank for some of the cloud analytics that we've done. We're very fortunate to Google and Amazon Web Services because we actually run our algorithms in their cloud to really demonstrate that there's feasibility. And we're also very thankful to UCSD, and there's a new medical center that's being opened up, co-founder of Qualcomm. So one of the co-founders of Qualcomm is in the audience, Andy Viterbi, and the other co-founder is a gentleman named Merwin Jacobs. And so these two gentlemen are basically the godfathers of wireless. And we're very excited because the godfathers of wireless are basically putting $1 billion hospital in San Diego that will allow for us to have medicine and cutting-edge technology. And so if you ever asked yourselves, what if Google were to build a hospital? Well, this provides an opportunity for us to attempt to explore that question. We're also thankful to a company named Airstrip. I didn't have a chance to talk about, but what's crucially important as we extract all this data is how do doctors make sense of this in a concise way that is not that different than how they're typically used to making decisions. And so they're developing some innovative ways to do that. Lastly, I would like to thank the National Science Foundation, the NIH, the Department of Defense, also Gerber, believe it or not. They have a foundation that funds research. Likewise, the Gates Foundation, Hartwell, as well as the Kavli Foundation. And so, to conclude, I guess where I am is I had this original paintbrush that was just the analytics paintbrush. I then went on to develop innovation with medicine, and then lastly, we developed this innovation with sensors. But the analogy I like to give to a lot of the students is that a lot of people get very excited about the cutting-edge analytics algorithms that we're doing or the cutting-edge technology that we develop with the sensors, but I always say proceed with caution. And the analogy I give is that if you gave Pablo Picasso 3 dull paintbrushes, he would make a masterpiece, whereas if you give an amateur painter 3 of the most sophisticated paintbrushes in the world, the painting is probably going to be nonsense. So it's always important that we focus on the painting that we want to make, and we use sophistication when necessary. And so there are equally as many projects that we pursue in our group that don't use all this cutting-edge technology as there are that do. That's important to remember. Let's not get infatuated with the cutting-edge stuff if we don't have a real use for it. And so in 1 minute, I would like to lastly shift gears and to talk about one other thing that we've been interested in at UC San Diego. And since we have a lot of K through 12 folks in the audience, we began to get interested in the engineering education problem. And some of you may have heard that there's about 10,000 engineers that we're not graduating enough of in America. And if you really stand back and you think about it, it's primarily for 2 reasons. We don't do enough engagement at the K through 12 level of what an engineer is and what an engineer does to create excitement. And also at the university level, a lot of freshmen that come in as engineers ultimately get pissed off after they get hit in the head with the math and the physics classes, and they leave. And so we got interested in trying to develop an approach that addresses both of those. And the high-level idea, first to explain to people what engineers do, is to think about social problems that everyone can relate to. And then from a social problem, let's ask ourselves, how does this affect our health? From that, how can technology be used to address that? That way we see that engineers solve all of our lifelong problems. Our approach is very unique in that it combines an industry perspective, a social diversity perspective, assessment, learning and assessment, so we really quantify whether or not our approach works, as well as an intersection of health and medicine. And we have projects going on at the K through 12 level, at high schools in San Diego. You can see MJ there demonstrating different things about the brain. We also have projects at the engineering, freshman engineering course, and we're very fortunate that some people from Intel actually come down and not only donate equipment, but also serve as judges for some of the experiential learning projects that students do. And the high-level model that we develop is to focus on the STEM from the perspective of social problem, how it affects your health, and ultimately how engineers address those problems, both at the high school level, the undergraduate level, both community college and university. We call this project the Fun Box. All right, that's what we titled it, Engineering and Art and STEM. And we're thankful to all the supporters from industry who donated devices for that project. And so with that, I would like to conclude by thanking the people who did all the work, our students. And as you can see, our students comprise some high school students, undergraduate students, grad students, and postdoctoral scholars. There's a lot of gender as well as ethnic diversity. But perhaps more importantly, what you can see is that there's a lot of diversity in training. So we have students from bachelor's degrees in bioengineering and mechanical engineering and electrical engineering, PhDs in biology, PhDs in neuroscience, and we bring everyone together. So with that, I conclude my talk. Thank you.
So you said you had high school students on the team. I'm just wondering, what exactly do the high school students in your team do?
Well, you'd be surprised. One of the reasons we really like working with high school students is that they can identify very novel uses of these types of capabilities. And so maybe they're not in the clean room dealing with wafers and doing sophisticated things like that, but they're identifying very unique projects where if you take these capabilities, you can address really important unmet needs. And so that is what I'd really like to enjoy interacting with young people, because you'd be surprised at the clever ideas that they come up with. If you had this capability and that capability, what interesting problems you could address. So we sort of outsource the creativity to the young people. Yes, sir.
What made you interested in this job? Like, what made you want to do this?
Well, when I was younger, I guess, when they give you some of these tests of basic skills, I ended up did very well in math and science. And so the teachers pulled my mom to the side and said that, he's really good in math and science. Make sure you take advantage of that. I was very lucky that my dad was in the school system, so he placed me in a high school where I got to go to my home high school half a day. This was in Dallas, Texas. And the other half of the day, I got to go to a science and engineering magnet high school. So I had the best of both worlds, sort of sports and prom at the home high school with my neighborhood buddies, but then going to study science and engineering. And I just knew I was good in math and science. I didn't really know, but you start to surround yourself with other people. You take different likings. Then when I got to college, I think the reason that I picked electrical engineering, to be completely honest with you, is because one of the cutest girls in engineering was in electrical engineering. So then, the point I'm trying to make is that you don't have to have it all figured out when you're 14 years old. You just surround yourself with smart people, have fun, follow your passion, and things seem to work themselves out. And seek out good mentorship. Like what my PhD advisor said, that very high-level wisdom, go delay your start date, do something wildly different. Always try to seek out people who are wiser than you, who have been where you are. And they're not necessarily going to tell you exactly do this, exactly do that, but they're going to give you high-level wisdom that's going to be very valuable. So, all right, well, thank you. Looks like you
Well, thank you very much, Todd. Allow me to read your certificate to the audience here. Todd P. Coleman is hereby honored as a recipient of the Gilbreth Lecturership in recognition of outstanding contributions to the field of bioengineering and presentation of his lecture on smart skin sensors and analytics at the National Academy of Engineering 2015 National Meeting. Todd, congratulations to you.